Hello all, I welcome you all to the 23rd lecture of this course EE690 ATM. The last time we met, we spoke about a superconductor, right? The superconductor is a material with a strong electron-electron interactions. A superconductor has some very important unique properties. The first one, it is a perfect conductor. What do we mean by a perfect conductor? Is that we take a material and then cool it down below a particular temperature. The resistance drops to zero or goes to zero, lower than what you can measure. In fact, they saw that there is an existence of persistent current. What do you mean by persistent current? Is that you set up a current in a loop. The current does not decay for a very long time, something of the order of 100,000 years. Right? The second thing, it is not just a perfect conductor, but it is a diamagnet. What it means is its magnetization is negative. Is negative. Why? Because it has to act opposite to what the actual magnetic field applies, right? So basically you take a normal material, apply a magnetic field, there will be some positive magnetization in the material, M, right? And it has to do with M is mu into mu dot B, right? Mu is the magnetic moment, dot B will give you the total magnetization, right? What is the orientation of the magnetization? Intrinsic magnetic moment with the magnetic field. Now, if you take a superconductor and put it through the same field, right, what will happen? The magnetic field starts to bend. Why does it bend? Because it ensures that the superconductor develops a negative magnetization here, such that this, when added to the magnetization due to the induced magnetic field, the total field H inside the material turns out to be zero. This is the origin of the perfect diamagnetism. So it's a perfect diamagnet. This is also called as the Masonry effect, right? This is what we saw. The third important property, that it has a gap in the density of states. This can be seen in ultrasonic sound absorption. It can be seen in electromagnetic radiations of low energy, right? These are all experimental observations. And fourth, the specific heat undergoes a discontinuous jump. The specific heat we talk about is the electronic specific heat, right? So let's say a normal material has a linear dependence of electronic specific heat. A superconductor at temperature T equal to Tc has a discontinuous jump up and then drops down even faster. This is a superconductor. And we are plotting specific heat versus temperature. Correct? So these are the properties that we saw. So today what we will do, we will go ahead and look at some sort of theoretical explanation for a few of these properties. We will see it in three folds. The first one is a thermodynamic explanation. The second one, we use a phenomenological model called as the Landau equations. And the third one, we see the Bcs theory. B for Bardeen, Cooper, and Schiffer. Right? It is also called as the microscopic theory. So let's go one by one. Let's look at the thermodynamic explanation for things. So for doing this, let's look at the magnetization. M is basically minus B by mu naught for a superconductor. Why? Minus, as we saw previously, it has to work against the applied magnetic field, right? So for that, let us consider a magnet, and there are fields emanating from a magnet, right? And I bring a superconductor from infinity where the magnetic field Ba due to this magnet is equal to 0. From here, I bring it to some point R, such that here Ba is Ba of R, some magnetic field, right? So what is the work done in moving this here? A work done inside the semiconductor conductor is the development of this negative magnetization. That's the work done, right? So total work done is obviously minus of integral m into dBA, 0 to BA. That is, I move the superconductor when field is 0 to a point where the field is BA, right? And whenever I move, the work done is proportional to the magnetization which the superconductor has to develop to support zero magnetic field inside the material, right? And from thermodynamic principles, the work done is the increase in energy. So the work done here, if I substitute m equal to minus b by mu naught, which will turn out to be integral 0 to BA by mu dBA, which will turn out to be BA square by 2 mu. And mu is obviously the magnetic permittivity of the material, right? If this is the work done, the total increase in the energy, increase in free energy of a superconductor total increase in free energy superconductor when a magnetic field BA is applied will be Fs is the free energy when there is a magnetic field, minus Fs when there is zero magnetic field is basically Ba square by 2 mu naught. So basically the free energy goes exponentially with the applied magnetic field Ba. Let's compare this. Let me plot this, okay? This is some free energy Ba. As we saw, it has to go exponentially, right? And this is the free energy of, let's say, the superconductor. Now, if I compare this with a normal material, Fn of a normal material, or the free energy of a normal material which is non-magnetic. If it is non-magnetic, then the magnetization m tends to 0, right? So the work done, as we saw previously, integral of my 0 to Ba m dBA will turn out to be 0. When the work done is 0, the change in energy is 0. Therefore, F normal of Ba will be the same as F normal of 0, which will be, let's say, some number Fn. Now let me plot it. It has to be always greater than 0, right? So let's say this is Fn. And it's easy to see that the free energy of the normal, this is the free energy of a superconductor, and this is the free energy of the normal material. It's easy to see that as the magnetic field is increased beyond a certain point Bc, which is the critical magnetic field, the superconductor has a smaller free energy, and above Bc, the normal material has a smaller free energy, right? So this is an important point. As the magnetic field is increased, there exists a field Bc where the normal material will have a smaller free energy. So this means the superconductor will stop being a superconductor beyond a particular magnetic field called as the critical magnetic field, right? and at B equal to BC, BA equal to BC, Fn equal to Fs equal to BC square by 2 mu naught. This is what we found, right? And the energy incentive between the normal material and the superconductor in the absence of the magnetic field is Fn is basically given by this value, right? In the absence of magnetic field, Ba equal to 0. So Fn minus Fs at 0 magnetic field is basically Bc square by 2 mu. This is the energy incentive between the normal material and a superconductor in the absence of a magnetic field, right? So this is an important derivation that we saw. And this is purely thermodynamic, right? So basically here we show that the superconductor is a new phase with a smaller free energy. This is the reason why there will be a phase shift at some particular temperature T. And Bc, as we know previously, also changes with temperature, right? And we saw that it goes like this. At T equal to Tc, Bc is basically 0. So basically there is no energetic difference. And as T reduces, the Bc starts to increase, and there is a larger and larger change incentive for a material to be in a superconducting state thermodynamically, right? So now we saw the thermodynamic incentive. Now let's go and look at some phenomenological model which explains or gives you some hold on the electric properties or transport properties of a superconductor, which is called as the Landau equations. Landau equations were derived mostly from the Maxwell's equation and the Drude's equation, right? So now let's take a look at our original Drude's derivation, where once again we are talking about electrons as classical particles like balls, right? And the Newton's laws of equation holds for these balls. So m being the mass of the electron, dv by dt the velocity, was given by E, which is the force, and Drude assumed a phenomenological constant called as the mean lifetime tau, right? This is what we saw previously. And if a material is going to be a pure perfect conductor, then the mean scattering lifetime is going to be infinite. There is not going to be any resistance, right? So for a perfect conductor, tau should tend to infinity, right? The scattering time is infinity. If tau tends to infinity, then this guy changes into m dv by dt is basically E. And in our previous Drude's model, we saw that the velocity will turn out to be E tau by m, and the current density J is given by Ne into velocity. So now what I'm going to do is multiply to this n into v, so which will turn out to be d by dt Ne into the v velocity is given by Ne square E by m, right? So basically in this equation I multiplied by Ne, and Nev, as we saw previously, is the current density. Dj by dt is Ne square E by m, which can be written as E by some capital lambda, right? So here in the event of perfect conductor, we see that there will be a change, or there will be a potential only when there is a change in current, right? It is like inertial term, right? So you do not have a potential when there is a constant current density. This is called as the first Landau equations, which we derived from very simple approximation from the Drude's law. So you basically need potential only to change the current density. And we have defined one parameter here, which turns out to be m by ne square, right? Now let's see how we can derive the second Landau equations, which is not very easy to derive, but we will try, right? So basically, from the Maxwell's equation, to or Landau's second equation, we know that del cross B can be written as mu naught into J, and here let's say I differentiate this equation by dou t. Del does not change into dou t of B is mu naught dou J by dou t, and dou J by dou t is basically E by capital lambda, which will give me mu naught E by capital lambda. And from the Maxwell's equation, we also know that del cross E is basically minus dou B by dou t, which if I will replace here, I will get del cross E will be minus, right, mu naught E by capital lambda. And del cross E is a vector identity, which will turn out to be del square E is mu naught by capital lambda into E, which I am going to write by E by small lambda square, where capital lambda is lambda square by mu, right? No. Basically, no. Basically, capital lambda by mu naught is lambda square, right? And so lambda square is m by mu naught ne square, right? So the solution to this differential equation will turn out to be E naught e power minus x by lambda, which tells you that if I take a material and then apply an electric field through this, the electric field will decay exponentially into the material, such that the electric field can only penetrate to some distance here, lambda, which is called as the Landau penetration depth. Right? So, given a superconductor and an electric field applied towards it, and of course, remember, we are not talking about DC electric fields. If there are DC electric fields, there cannot be there is no DC electric field inside a superconductor, right? So if I take an AC electric field, the AC electric field decays exponentially inside a superconducting material. So Landau's equations are also sometimes called as Landau electrodynamics. In the similar fashion, one can also prove that, say, if I take del cross B is mu naught J and then go through similar equations, I can also prove B can be written as B naught e power minus x by lambda, which shows that the magnetic field also decays exponentially. So I take a superconducting material and apply through this a magnetic field. The magnetic field will decay exponentially, leaving a very small region in which the magnetic field resides. And in this region where there is a magnetic field, it's easy to see that del cross J is minus B by lambda, which tells you that if there is a magnetic field in the superconducting material, there is a circulating current through this material. So there will be a current which circulates, and this circulating current actually generates a magnetic field equal and opposite to the external applied magnetic field, which causes these guys to bend. Right, this causes the magnetic field lines around a superconductor to bend. This is because there will be a circulating magnetic field in the superconducting medium. I'm not proving these expressions for you. I can actually put it for your homework, but it just will take 2 lines, right? So 2 things that we have proved. One, the magnetic field in a superconductor decays exponentially. So this tells you that there is no magnetic field inside a superconducting medium. One. Second thing, there exists what is called as a screening current. Because there is a small penetration depth inside a superconducting medium, there is some screening current which goes through this medium, and this screening current actually screens all the magnetic field that is present, right? So this is what is called as the second Landau equation. The length lambda through which it decays, lambda, is basically m by ne square mu power 1 by 2, and this n here is called as, or n or ns is called as the number of superconducting electrons. Right, Landau was a phenomenological model, so he did not basically distinguish between electrons which are superconducting and electrons which are normal materials, right? So it has to wait for another phenomenological model given by Ginsberg and Landau. Who basically showed you what this ns, the number of superconducting electrons in a material, which makes it to be a superconductor, right? So basically Ginsberg and Landau introduced this pseudo wave function. So typically wave functions are written for one single particle, for one single electron, right? And Ginsberg and Landau, they showed that in a superconductor, it is a many body wave function, in the sense that you cannot treat the electrons in a superconductor as a single particle. It is a collection of all such electrons, and the number of electrons in this many body wave function can be written as ns is the modulus of psi s of some r square. So basically he showed that this is the typical behavior, whether the probability to find an electron or not, right? So basically this is the number of electrons is proportional to the magnitude of the wave function square, and the wave function has to satisfy an equation which is called as the Ginsberg-Landau equation, which is very similar to the Schrodinger's equation. So basically they wrote down these equations without any solid proof, but they were able to prove a lot more properties of a superconductor based on these equations, right? So basically that's why it is also a phenomenological model. There is no fundamental background derivation for these equations. It is just it's just empirical, right? So the equation which this wave function psi of s, which describes the number of superconducting electrons, is written as 1 by 2 m star. Of course, this m star is the mass of the electron, right? But then it is not just an electron, but it's a many body wave function. H by I delta, obviously this is the momentum, minus E star A. Here remember the charge E is also not the normal electronic charge, but then this is E star. This is a charge of a superconducting many body particle, right? And A being the magnetic potential. So this transformation we saw previously in our derivations, right? Whenever you have an electromagnetic interaction, the momentum is transformed into momentum minus E star minus EA, right? This is something we saw. Momentum square into psi s plus, now this is an addition. Now you have a nonlinear part, some beta psi s square into psi. So this is an additional part in the Ginsberg-Landau equation in comparison to Schrodinger equation, which should be given as minus alpha of t. Alpha is like our eigenfunction, and psi s. And here the current, once again, as in the case of the Schrodinger, one can write the current density, which is superconducting current density, is given by E star H cross by I2M star psi s star del psi s minus psi s del psi s star. This is something that we saw previously in the normal electron case as well, right? This is the change in the probability density function. Minus E star square by M star psi square into A. This additional component comes because you have an additional component which acts like a potential term in a Schrodinger's equation, right? And they showed that using this this phenomenological model, they showed that if you solve a Schrodinger's equation, then if I take a material such that, let's say, on the left hand side you have a superconductor, and on the right hand side, let's say, you have air or a normal material or whatever have you, then the modulus psi s square changes in this fashion, right? So basically the superconducting density of electrons, let's say if this is the surface, it reduces in this fashion from the surface to the bulk, which also explains why the magnetic field in a superconductor dies exponentially down from the surface. The same thing happens also to the electric field, right? The electric field and the magnetic field, everything dies exponentially from the superconducting surface. And they showed that this is because the superconducting density of electrons decays from bulk to the surface in this particular fashion. And here, when you know that this is the Landau penetration depth, they defined what is called as the coherence term, which is eta, and they showed that the eta, or Ginsberg-Landau coherence length, which is a function of temperature, was written as H cross by 2m star alpha of t. Alpha of t was the eigenequation of the eigenvalue of the Ginsberg-Landau equation, as we saw previously, right? So this is a small derivation, a small representation of electrons in a superconducting medium, right? So he used just the Schrodinger's way. He developed a wave function psi, and then showed that if this psi is shown to solve an equation of this particular term, then if you plot the psi, it can tell you what is the density of electrons which behaves in a superconducting fashion inside a normal material, right? So this is the second phenomenological model, which is called as the Ginsberg-Landau equation. Now we have come to the last part, which is the microscopic theory. Now let's take a look at the microscopic theory. Also called as the Bcs theory. So a lot of assumptions have been made to understand how each of the independent electrons in a superconductor behave, right, when they transition from the normal material to a superconducting state. So you consider a Fermi C or a gas, as we saw previously in the Landau's treatment. So this is the K space, and some spherical region determined by Ky, Kf, under which all the states within this sphere are occupied, right? Now let's take an electron pair K and minus K. Cooper, Bardeen and Schiffer, so they considered electron pairs such that their total momentum between the, let's say, K1 plus K2 almost equal to 0. So states like K and minus K, K prime and minus K prime are the electron pairs which they considered, right? There's a reason for this, we'll come to that later on. So if you take these electron pairs and they assumed a potential V such that they scatter electron pairs with momentum K and scatter them to K prime, right? Let's say this got scattered to K prime and this got scattered to minus K prime. The essential part of this is that the center of mass momentum does not change, right? K and K prime have 0 center of mass momentum. K prime and minus K prime have 0 center of mass momentum. So they assumed potential V K K prime such that this particular scattering is prominent, and this scattering is negative. So basically we have an electron-electron interaction where the potential is negative, and a negative potential means an attractive force, right? So consider a normal Coulombic repulsive potential where the potential will be positive, right? 2 electrons with 2 negative charges, the total potential will be given by E minus E into minus E by 4 pi epsilon r, right? So basically you have a positive potential if you have a repulsive interaction. When you have a negative potential, you have an attractive force, right? So basically he assumed that there exists an attractive interaction between 2 electrons. The origin of this attractive interaction we will see later on, but if you take this particular interactive potential, BCS were able to prove that there will exist an energy state which will be smaller than sum of these 2 energies, right? So now let's say you take 2 independent electrons, their energy will be twice the dispersion energy, right? And dispersion energy is basically h bar square k square by 2m. Now I take 2 electrons with plus k and minus k. This will be the total energy, right? Now if we turn on this interaction, what will be the energy? Let us take a look at first the wave function. Psi of such an electron is or can be written as some center of mass component rho and e power I q dot r. So this is the relative component and this is the center of mass component. Q is k1 minus k2 between the 2 electrons. Rho is r1 minus r2 and r is r1 plus r2 by 2. This is the wave function of any 2 electron particle. Now we are taking some special privileges. So we are taking q almost equal to 0. Under such situations you can clearly see that the center of mass motion, that is this particular exponential part, will turn to 0. So this is the reason why BCS took electron pairs such that their center of mass motion tends to 0. You have 2 electrons whose k vectors are equal and opposite, right? So basically then you can take this psi is basically q of rho, which is a function of just r1 minus r2. And there he wrote this as summation over all k's gk cos k r1 minus r2. So basically he expressed the function as a Fourier series expansion in cos. Because they want the wave function to be symmetric, they took only the cos component. Typically you can do this even with the sine component, it should not change. Now if you substitute this into the Schrödinger's equation, where the total Hamiltonian is written as the unperturbed Hamiltonian H plus this new scattering potential V that we talked, which will scatter k and minus k to k prime and minus k prime, right? And you use this Schrödinger's equation E psi, and which will turn out to be V psi is E minus H naught into psi and E minus H naught is E minus 2 epsilon k, because there are 2 electrons into psi V psi, right? And you can write, if I substitute the psi into this equation, I will get summation over all k prime V k k prime G k prime will be equal to E minus 2 epsilon k Gk, right? So now nothing has been assumed about this potential, and this is where their second approximation comes, which is called as a spherical approximation, where they assumed that the potential V, which scatters k to k prime, is constant for some region from the Fermi level EF, which they call as h cross omega c, right? And it's a constant to that region. So their assumption is V k k prime is some negative potential, means attractive force, as we saw previously, right, is negative V for k smaller than omega c, and for k larger than omega c it is actually 0. So basically there is no this pair scattering potential for wave vectors larger than a particular threshold, and for a wave vector smaller than the threshold, then the scattering potential is constant. Under this situation, this expression can be easily simplified, which will give you this E is 2 epsilon k minus V summation over k prime G k prime by Gk. And a few steps will actually easily give you epsilon k minus 2 h cross omega c into e power minus 2 by n being the density of states at the Fermi level into V. This V is the negative potential that we previously described, right? And this part is a crucial part, which is described as the superconducting order parameter delta is h cross omega c e power minus 2 by nb. N is the number of density of states at the Fermi level, right? So here we have proved that, or if there is an attractive potential between two electrons, then the total energy of the electron pair is smaller than the individual electron energies, independent summation of two independent electron energies, by a particular value delta. This is the reduction in the total energy, thus leading to a bound electron pair state, right? This is the origin for a superconductor. So let's say the visual understanding of this can be something like this, right? So let's take a material and you introduce an electron. This electron kind of pulls the positive ion cores towards it, right? It just slightly alters the positive ion core in the neighborhood of this. So what it means in the Feynman's picture is, I take K, an electron, gets scattered to my K prime and release a phone on Q. This arrangement of ion cores releases a phone on Q, right? And this arrangement of electrons or ion pairs will attract another electron towards it, right? Because there is now excess positive charge closer to this electron. This additional electron now brings two pairs together, localized in this region, right? It can be visualized as minus k getting scattered to minus k prime, right? So the positive interaction between two electrons is only possible if there is a mediation using a phonon, and this mediation using a phonon is initially what was called as Froelich interaction, but this is the origin for the Bcs theory of superconductivity. Okay, so this reduction in the total energy, the order parameter, is observed in many places. The first thing is the energy gap or the excitation. Excitation energies are given as so the excitation energy starts from a gap of delta K. This is the reason why you have absorption H cross omega, right, is 0 for some energies below energy delta, and at delta there is a sharp enhancement in the absorption, and then which reduces, right. This is practically observed absorption in a superconductor. In addition to that, the density of states is expressed like this of a superconductor. Of a normal material goes as root E, right. For a superconductor, let's say if this is EF, the density of states, this demonstrates a gap. Which means that all the electrons in these energy levels form a bound state at the Fermi level called as a Cooper pair state. It is called a Cooper pair state because we only talk about electrons which are minus k and k, which are equal and opposite in the momentum, right. Only these electrons form a bound pair state whose energy is lower than the summation of two individual states, right. And this formation of this bound state gives you a gap in the density of states very close to the Fermi level of magnitude 2 delta in each side, right, of magnitude 2 delta. This is observed in conductivity measurements. So if I take a normal metal and interface it with a superconductor, normal metal has a Fermi level here, and if I interface it with a superconductor whose density of states looks like this, close to the Fermi level, this is the Fermi level. So this is superconductor, this is normal material, right. The IV characteristics will look like this. Till the potential is lesser than delta, there is no conductivity because there is no density of states. When the potential is equal to delta, then there is an exponential increase in the conductivity, right. This can be contrasted with a normal diode. Diode also has similar behavior, but the diode goes like this, right. But for a normal metal semiconductor junction, the conductivity increases exponentially because there is a diverging density of states at the edge of the superconducting gap, right. Yeah. All right. So we saw that if you have an attractive potential minus V for some energies given in this fashion, then you will have the pair energy smaller than individual summation of two individual energies, and the magnitude of this reduction is the gap in the density of states, right. And if you have a gap in the density of states, that can be seen experimentally in the absorption spectrometer, in the absorption spectrum, as well as in the tunneling spectroscopy. Now we will very briefly see what can be the origin of a positive attractive potential. We know that the potential energy in the Fourier space, okay, between two electrons is given by E square by 4 pi epsilon Q square, right. This is the potential or the Coulombic repulsion between two electrons. However, if the potential is screened, and we know that V of Q can be written as E square by 4 pi epsilon q square plus some kx square. This is an additional term just to show that your screened potential is smaller than the unscreened potential, right? So this ks is just an additional term. In the previous case, we saw that you have some e power minus lambda r kind of a behavior. This is in real space, but we're talking about in Fourier space here. So it behaves in this fashion, right? So if in addition to the screened potential, if there is some interaction with some phonons, people have shown that the total potential is now a function of both the phonon frequency omega as well as the frequency of scattering, which is given by e square by 4 pi epsilon q square plus kx square into omega square by omega square minus omega q square. Now, if this is the Coulomb potential, it's easy to see that this can turn negative when your the energy of the phonon is smaller than some value. So this, as long as your phonon energy is smaller than some threshold value, you can have a negative interaction, and it is this threshold value is what we saw in our definition here, h cross omega c, right? Now the derivation for this potential actually comes up from what is called as a Jellium model, but we will not go into such details right now. But all we are trying to say is, if you have electron-electron scattering in a screened potential in the addition of phonons, you can have a negative interaction between electrons, which is phonon mediated. The attractive interaction between two electrons gives you a bound state which has an energy which is smaller than two individual electrons, energy of two individual electrons, and this bound state gives you a gap in the density of states, and the gap in the density of states will give you this the spectrum of electromagnetic absorption as well as this tunneling conductivity as seen here. Alright, so with this we will stop our discussions on superconductors. We saw some very basic principles. We saw about Josephson's junction, we saw about the Meissner state, we saw about zero conductivity, we saw the Landau's equations, we saw Ginsberg Landau phenomenological model, just the basic aspects of these things. And with this we will close our chapter on superconductivity, and this will be the last recorded lecture for this course. The conclusion and summary part, we will have it during the interaction session. Thank you.